All right. So what I want to talk about now is some applications of elementary mathematics to cryptography. So cryptography is a huge subject. There's an enormous amount of stuff we can do. I want to try to just talk about a few of the key ideas and give you a little bit of a sense of what mathematics we need. And so amazingly, a lot of the mathematics we need is extremely elementary mathematics, stuff at the level of elementary school, but just done really well. And so this ties us back to this notion of efficiency. It does you no good if it takes you, 12 hours to decrypt a message if this is a message that needs to be acted on immediately, such as, hey guys, you're shelling your own troops, please redirect your fire. That's a message that has to be decoded very quickly. If it's a longer term assignment, such as, here is an update on the plans for D-Day. If it's in the plan, it's okay if that takes 12 hours to decipher. And so depending on the level of information, you have different amounts of time that you're willing to allow the encrypt to decrypt. Great examples to talk about the wind talkers, the Navajo Indians in World War II. And one of the whole points of that was to be able to communicate in real time in such a way that the enemy could not interpret what was going on. And you had to have really fast ways to encrypt and decrypt. Whereas, for other things, you wanted a very high level of security, even though, of course, the Navajo code talkers was very secure. Lots of great stuff about World War II, the Enigma, the Ultra, the attempts by the Allies to successfully crack the German Enigma. There's not enough time in 15, 20 minutes to get into all of this. But if you're looking for students about mathematics, this is wonderful. Did I talk about the Battle of Midway in the last class? This is one of my favorite examples of elementary mathematics making a huge difference. So we knew the Japanese were going to attack, I think it was AF-15. We had cracked their code. Or we had cracked enough of their code to realize that they were going to attack something designated as AF-15. Unfortunately, we weren't sure what AF-15 was. It could have been Midway, which was what we thought. It could have been Hawaii. It could have been Australia. It could have been Alaska. There were a lot of different possibilities. And so if you're the US Admiralty and you're trying to decide where to put your forces, if you are 100% sure that the Japanese are going to attack Midway, you can lay a trap for them. And in fact, Midway, the US chose to do that. This became the turning point in the Pacific War. Before the battle, the Japanese had naval supremacy in terms of aircraft carriers. After the battle, we had supremacy. They lost 4 aircraft carriers to 1 of ours. It was absolutely devastating for their forces. We needed to be sure that AF-15 meant Midway. Well, one possibility is you could call up the Japanese and say, we've intercepted some of your messages, but we're not quite sure, does AF-15 mean Midway? It's the fastest way, but there are some obvious issues with this approach. They did something beautiful. I believe it was Commander Rochefort, I'm not positive, who had the beautiful idea of, on a secure channel, telling Midway to break one of their water pumps. And then over a non-secure channel, or using a system that the Japanese had already broken, Midway was then giving a generic status report. And in the list of things, they said, in the next resupply run, please make sure you include a water pump. Our water pump is broken, and if we don't have a replacement, we'll be out of water in 2 weeks. Shortly afterwards, they intercepted a Japanese message saying, we've overheard that AF-15 has a broken water pump. And so they got the Japanese to admit to AF-15 being Midway. Any Babylon 5 fans here? All right. Another science fiction show. There's a great episode where they do something very similar here, where they deliberately get the enemy to give up information. And so a huge part of cryptography is the science of deception and playing games like this. As a Red Sox fan, the following is a little bit painful to talk about, but the Kyle Crawford contract, when we got him from Tampa, who else was interested in signing Crawford? Not the Dodgers. It's a trick question. The Yankees were not interested in signing Crawford, but they gave the appearance they were to drive up the price. And so if the Sox knew that the Yankees were bluffing, we would not have given him nearly as much money and tied up nearly as much of our funds on him. So in terms of trying to find units to talk to students, I've written some modules on using cryptography in classrooms. And if people want, I'm happy to share these modules. There's a lot of great stuff going on.
It's also kind of like what they talked about with some of the cyber attacks, or sometimes getting it. The biggest key to break it through the computer is when somebody tells you one piece of a password.
Yes.
In other words, it's not that they're searching every permutation
Right.
to find out.
Oh yes. In World War
II,
there was a German station that always began the day by broadcasting the weather report. And knowing that gave you a real head up on cracking the code. Now, the Germans made a couple of small mistakes with Enigma, which were exploited. If they had used it perfectly, I don't think the Allies would have successfully cracked it. But the estimates are Enigma shortened the war by 2 years or swung it from a Nazi victory to an Allied victory, in terms of just knowing what the Germans were going to do. I wrote a cryptography book with a colleague. In addition to dedicating it to members of our families, we dedicated it to the men and women of the armed forces who gave their lives to gather and protect the gathering of this information. So for instance, in World War II, we often flew reconnaissance missions to find out where the German fleets were or the German transports were. And a lot of times these pilots were shot down. But we already knew from cracking the German Enigma where the fleet was. Why would we bother flying planes?
So they would think that you didn't.
So they would think you didn't crack. So the rule was you could never do any action where the only way to explain how you knew to do this was by cracking the German code. You always had to give, you always had to give the Germans an explanation as to why you did this. Oh, look, plane flying overhead sees us. That's probably how they know where we are. You might do a little bit better than you might be expected in terms of which routes the pilots choose to fly.
Do you think the pilots knew that?
No. Absolutely did not know. You cannot risk the fact that the code was compromised. And in fact, there were times when certain commanders did not have knowledge of where this came from. And they had, hey, trust HQ on this. Reinforce your center flank right here.
Line of command.
Line of command. And if you trust your superiors, you do certain things, and you do things in such a way that things work out for you. But it can't work out for you all the time. And there are times when you have to have losses. The Germans were fooled. Patton hit an enlisted man, and he got demoted. He was in the doghouse for a while. And when we were planning the Allied invasion of Germany, the Germans couldn't believe we would remove one of our greatest military commanders because he hit an enlisted man. This is war. And so they said, well, okay, well, if you can't believe that, let's create a fictional army around Patton and plan to invade not at Normandy, but at Calais. And so this was called Operation Fortitude. And Hitler kept certain German divisions in strategic reserve near Calais so that when the true landings happened, they would be ready and available. And so this art of misdirection is huge in cryptography. There's only so many topics we can discuss in 20 minutes. I'm trying to give you a sense of other things that you might want to work into your classrooms in terms of trying to excite students. World War II, fortunately, we're not having these massive land wars anymore, but we are negotiating with the Yankees in terms of signing players. And this idea of misdirection about how interested are you in signing Carl Crawford and stuff like that, this is important. So for many years, the gold standard was RSA, named after 3 mathematicians who came up with a way to allow 2 people who had never met to quickly and securely exchange information. Yes. It's getting late in the day, so I'll go like this. All right. So this is an amazing discovery, and for a long time people thought it was impossible, that all methods of cryptography relied on 2 people meeting ahead of time and agreeing upon a secret key. So if Henry and I want to have this correspondence as to who's going to pay for lunch, why don't I pay, why don't you pay? We can do this in secret with you guys not knowing it because we've met before and we have the secret key that we've exchanged. Some strange password or whatnot that we use to build a crypto scene that's known only to the 2 of us. And because we've met many times, we have this secret password that we can use that other people don't know. But what if all of a sudden I have to communicate with somebody I've never met before? So can you give me an example of a situation where you need to communicate with somebody you've never met before? Online. Right. This is e-commerce. Right. Most people have not walked into Amazon HQ or Target HQ or any of these stores and said, I'd like to talk to one of your branch managers and introduce myself and set up a way for me to securely pay online. you take out your credit card, you put, or better yet, Henry's credit card, and you just, charge things. That's the best way. And you just charge things. And you have some expectation that this information is going to be securely transmitted so that only the two of you know, but you've not agreed upon a password ahead of time. So rather than going through all of the mathematics behind this, what I thought I would do, because of approaching Storm, is say, I have a computational module written for high school students, which I will just give to you, which has all this stuff explained in great detail. If you want more, I wrote an elementary book on cryptography for liberal arts students. Happy to give you links for stuff like that. And I'll just give you a rough sense now of what's going on. I will give the original version of the problem. It's the sexist version, but it's the original version and homage to it. I will go with the original version. All right, so we have two islands.
What does RSA stand
The initial Rivest, Shamir, Adelman. So here, in my horrible, horrible drawing, two islands separated by water. Thank you. Here's two people. She has red hair. And we will make the following assumption. This is a Red Sox fan who went to Williams College, a catch. And so if he asks anyone to marry him, of course they'll say yes. All right? No brainer. Especially when you have this beautiful orange carat ring. The only problem is, of course, that she will never accept a marriage proposal not accompanied by a ring. She just wants to make sure that he is who he says he is, that he has the resources and whatnot. He's got to get the ring to her. Unfortunately, they're trapped. Luckily for us, there is a pirate ship. Okay. So,
Not the Black Pearl?
no, it's not the Black Pearl. We'll see who knows why it's called the Revenge. The Revenge. Nope. Nope. The Dread Pirate Roberts.
Yeah. That was his boat?
That was his boat. From Princess Bride is the Revenge. So you have a pirate ship which can sail between the two islands, and because they're pirates, they're not completely trustworthy. But we know from the Princess Bride that the Dread Pirate Roberts is not a horrible guy. And so he has a box, and this box has two locks, and he has his lock, and she has her lock. And so each one of them can lock it, only one of them can lock it, neither one of them can lock it. And the pirate ship will transmit things back and forth between the two islands freely. If the ring is in a locked box, the pirates will not touch it. If the box is open, well, this is just too much temptation. And of course, they're going to ring, and they will just take it and add it to their pirate booty. So he's got to get the ring to her in a locked box. But she's got to be able to open it, and their locks are different. So how can he get the ring to her? So I hope it's clear why this is in some sense a model for cryptography. We want to transmit some information. The information is the ring. We have a very insecure system. And we have to do everything in public. This has been likened to two people agreeing upon a secret, screaming in a room where everybody else is silent and listening to everything they're saying. So all the snoopers, all the bad guys can hear every word we're saying. And at the end of the day, Henry and I will agree upon a secret. Any thoughts as to how he can get the ring to her?
It's like that problem with the wolf and the rabbit and the cabbage and the boat, right?
Yeah, get it back.
It's similar. You've got to go back. It's very similar to, it's of the same. Yes.
And then she sends over her log.
Okay, so it starts off with empty box. So
But with a lock.
empty box. So this is Bob. And this is Alice. The names are fixed. Empty box at Bob. And what does Bob do?
And it's open right now?
And it's open.
You put the ring in and locks it?
No, he
Adds ring.
The lock
So he adds his ring and adds the ring and locks it. And so now Bob's lock is on, and we have the ring inside. Locks, and now sends to Alice.
She's got to lock her lock, but she's got to lock her lock.
Yeah, I mean, there's nothing else she can do. Great, I've got this locked box. If I don't do anything, well, then it just goes back to Bob, and I've done nothing. So the only thing she can do is she locks it. So Alice locks.
But then it goes back and he takes his lock off.
Yes,
And it goes back
and sends to Bob. So now it comes to Bob with 2 locks and the ring. So now Bob removes his lock, sends to Alice, who removes hers.
And the ring.
Okay?
Quite a marriage they're going to have, these two islands. Lock it off.
It might actually be an advantage for them to be on 2 different islands, but that again is above my pay grade. So here is a way for them to exchange a secret. And they've done it in a very insecure manner. So the idea behind this riddle and the solution is the basis of all of e-commerce. So when you're talking to your students who want to know, give me an application of why might I care about something like this. And if you've ever bought something online, that's an application of this. So you need ways to agree upon a secret without actually meeting. And so one of the ways of doing this is it's called RSA. And for years it was the gold standard. There's other algorithms that are now faster and more efficient, but it's a very good algorithm. Classically, it's extremely important. It allows 2 people who have never met to communicate in secret. And this was a revolutionary advance in cryptography. It was something that a lot of people thought could not be done. You've got to physically be together to exchange a secret. Now the question is, how do you do this in a mathematically nice way? Other ways that this is described is you have some paint. And so the paint description, how do we do this?
What is RSA?
RSA is a way for 2 people to communicate in secret who have never met. So there's many different components to RSA. And so there's the need to transmit information quickly, there's the need to decrypt it quickly, there's the need to make it secure, and there's the need to not have to meet ahead of time to agree on a secret. And so the paint way of phrasing this is you have some jar, again I don't have that many colors so I apologize, with some kind of paint color inside. Okay? And so you have this jar of paint, and you give some to Bob, and you give some to Alice. And then what Bob does is Bob adds his color, and Bob chooses a color, color B, Alice chooses a color. Bob adds his color and sends it to Alice. And when Alice gets it, what do you think she does? Adds her color. Alice adds her color and sends it to Bob. What do you think Bob does? So, I'm sorry? You can't. There's no easy way. So what you do is you have the original plus A plus B. You have this new mix. And one way to get the new mix is Bob takes some of the original, adds his color, sends it to Alice, who adds her color. And so
He takes some of the original out.
he takes some of the original out. And the way Alice does it is she takes some of the original, she then sends it to Bob, who adds his color. So both Bob and Alice now have this new color. And if you intercept in the middle one of these transmissions, there's no easy way to subtract a color. So this is the paint explanation for what they're doing. So it's a way for them to agree upon a shade. Okay, and if you want, you can now look at the RGB triple of that color, if you want, and that's your code phrase or something.
So if you found it somewhere in the middle, you're only getting part of the message.
You're only getting part of the message, and there's no easy way to figure out how to remove a color, because we don't know what Bob's color was. And so again, this is just one way of trying to explain what's going on without all the mathematical stuff. In terms of e-commerce, this is not going to work. We're not going to be FedExing tubes of colors back and forth to stores. It's not fast. It's not good. So in the computer age, instead of sending messages like hi, we send strings of zeros and ones. And we use zeros and ones to represent information. You can always do some kind of correspondence. You can have 0, 0, 0, 0, 0 equals A, 0, 0, 0, 0, 1 equals B, 0, 0, 0, 1, 0 equals C, and so on. And if we do something like this, if we can just exchange sequences of zeros and ones, that's the same as sending messages. So now the question is, how do we do this RSA thing? How do we allow Alice and Bob to communicate quickly and efficiently without knowing a secret? So in the first class, we talked about Horner's algorithm. And Horner's algorithm allowed us to evaluate polynomials far faster than we expected. Rather than taking on the order of n squared multiplications, we did it on the order of n multiplications. So we're going to do something similar. It's called fast multiplication. So let's say you want to calculate x to the 100. How many multiplications does this cost? 99. Because x squared costs 1 multiplication, x cubed costs 2. So if I have a huge number, and in RSA, these numbers are not small numbers like 100, we raise this to a 200-digit number. They're huge. You can do this in a lot less than 99 multiplications. X times x is x squared times x squared, x to the 4th times x to the 4th. And this is why I always hate, why do I always do 100? X to the 8th times x to the 8th. I know, x to the 16 times x to the 16 is x to the 32. The last one is all I need. X to the 32 times x to the 32 is x to the 64. What I do is I write 100 in base 2. So 100 is 64 plus 32 plus 4. So one of the things we've talked about several times over the past 2 days is different systems for decomposing numbers. I look at the base 2 decomposition of 100. Well, if I now want to get x to the 100, that's x to the 64 times x to the 32 times x to the 4. If I want to count how many multiplications are needed, 1, 2, 3, 4, 5, 6 to get here, 7, 8. So I can do it in 8 multiplications. So it leads to 8 multiplications. In general, it's about at most 2 log base 2 of your number, if you want to calculate x to the n. Much, much faster. Rather than needing on the order of n multiplications, you need on the order of log n. If n is 10 to the 200, 10 to the 200 is beyond what we can do. There's 10 to the 80 thingamajigabogs in the universe. We can't do anything of size 10 to the 200. Log of 10 to the 200, oh, that's 200 log 10. Log of 10 is about 2.3. We're talking about something under 500. Under 500 we can do. So this whole idea of fast multiplication allows us to handle things very quickly. So we can do a lot of calculations easily. So this is one of the first key steps in making RSA work, the ability to calculate high powers of numbers well. Okay. The whole idea behind RSA is you take an algorithm that you think is hard to do unless you have secret information. How many of you have seen Monty Python and the Holy Grail? What's your favorite color? Blue! Blue! So in Monty Python and the Holy Grail, you have the God who's on the bridge who's only letting certain people go. And he's asking you questions, and he recognizes when you give the right answer or not. And if you give the right answer, you get in. So here's 2 different systems. In system 1, the password is P times Q. P and Q are prime, and they have about 200 digits. In system 2, you take a random string of 5,000 digits. Which do you think, and the password here is P or Q. If you give me either one of them, I let you in. Because if you know one of them, you know the other. Over here, you have to give me all 5,000 digits correctly. Which do you think is harder to guess? 200 digits correctly or 5,000 digits? So which method would you want to use? The first one. Well, second one, doesn't this seem more secure? There's 10 to the 5,000 possibilities here. There's only 10 to the 200 here. This is far more secure, right? Yeah, we don't want to do that.
See, I was right.
You were right, of course. Whenever a professor's asking a question like this, it's, why is this such a bad idea? So,
It's easy to make a mistake.
well, no. I mean, how does the computer know if you're correct?
It takes a long
It has to check. If the computer is checking, it needs to know the password. Geneva Convention does not apply to computers. If you capture a computer, you may torture it. You may do whatever you want. The information is on the hard drive. You can extract it. Over here, does the computer need to know the password? No. Computer knows the product P times Q. And it knows how to divide. This is the, I'll know it when I hear it. What's the password? You give me a candidate, I'll check. Does your number divide my product? If yes, okay, you knew the password, come on in. The advantage here is you do not need to know the password. You can have a dumb sentry. Whereas here, you have a sentry that you can torture. So in terms of security, this is far more secure. Even though it looks like there are far fewer possibilities here, yes. But 10 to the 200 is still so many. It's still so huge, you're okay. And here you have no possibility of torturing the computer.
But only if you don't know that that's the system. If you know that we're talking
Sure.
about the product of time, you get your computer.
In a lot of the real-world applications, you actually know the system being used for encryption.
Yeah.
So that's not a horrible assumption that we know what's going on. The difficulty is factoring. So is it easy to multiply numbers?
Yeah.
Does anybody want to multiply two 200-digit numbers on the board? No, okay. So there's a difference between easy and fun. All right. No one wants to, but if your life depended on it, you could do the multiplication. It would be time-consuming for us. For a computer, not at all. The computer can easily multiply two numbers. If I know one of the numbers, I know the other.
Yeah.
The difficulty is if I give you the product, we don't know a good way to factor. There may be a good way to factor, but to date, no one has publicly disclosed a good way to factor. So it's believed that multiplication is easy and factoring is hard. And they've built RSA around that idea, that factorization is difficult. So because factorization is difficult, this seems very secure. So again, this is the blitzkrieg introduction to RSA. But this is the key idea, is you take a process that is easy to do if you have a cheat. If you know one of the two primes, it's not so hard to find the other. If you don't know one of the primes, we don't know any easy way to factor. So roughly, this is how RSA works. Choose big primes P, Q. I'm going to let n be P times Q. And there's a special function called phi of n, Euler's totient function, which I'm not going to get into too much right now, which is equal to P minus 1 times Q minus 1. And again, if I know P and Q, it's very easy to calculate these things. And the idea is the following. If you want to send M, let's see, Alice chooses E and D such that E times D equals 1 mod phi of n. So what this means is, we were talking about clock arithmetic last time. What's 10 plus 5 on a clock? 3. Right. So 10 is equal to 3. I'm sorry. 10 plus 5 is equal to 3 mod 12. So we now imagine our clock has p minus 1 times q minus 1 hours. And so I choose two numbers e and d such that e times d equals 1. So the first question is it hard to find such numbers? Turns out it's not. There's something called the Euclidean algorithm, which some of you may have used to find least common multiples. Or, I'm sorry, greatest common divisors. So using the Euclidean algorithm, you can actually find these. Use Euclidean algorithm given an e relatively prime to phi of n. You can then basically find a corresponding d. So I'm not going to go into the details. If anybody wants to, this is all written up in great detail. There is a way to find e and d fast such that the product is 1. So Alice makes public the following: p times q and e for encrypt. And she keeps secret p, q, and d. So the entire world knows the product, and the entire world knows e. But we don't know phi of n. We don't know p minus 1, q minus 1. And right now, nobody knows a good way to find that given this. We know e because Alice has told us e, but we don't know an easy way to find d. We're trying to solve this equation where we don't even know what this number is. I don't know how many hours there are. That makes it a little bit hard to find d, right? I want to find the number which, when you multiply by e, is equal to 1 modulo the hours. Not going to happen. So how does this work? All right, well, Bob sends the message m to the e mod n. So think of m as a 200-digit number raised to a 200-digit number. But we're only sending it mod n. And so what you do is, as you do the fast multiplication, every single time you multiply, you reduce modulo n. And this keeps this number from growing too large. It's never larger than 200 digits, or 400 digits, because that's how big n is. So Bob sends this to Alice. Alice computes m to the e mod n to the d, which turns out, after you do a lot of algebra, to be m to the e d mod n, which turns out to be m mod n. It is absolutely amazing the amount of magical simplification that happens because this is 1. And so, again, I have detailed proofs of the algebra of how you would show that this reduces to that. The whole point is everything that's being done can be done very rapidly. And it's using elementary algebra. It's using it in a damn clever way. It was not easy for people to come up with this. They went through an enormous number of attempts before they found something like this that worked. But the idea is, at the end of the day, Bob has sent a message to Alice. And let's say the message is, Alice, I'm in a real jam. I need you to send me $5,000 to the following Swiss account. Love you, Bob. What does Alice do?
Send your ring back.
So why does Alice send her ring back? So why does she send her ring back?
Doesn't have $5,000.
Oh, Alice has $5,000.
Fake him out.
I'm sorry?
Fake out somebody.
Well, what issues might Alice have?
Well, she just sends the. She know for sure.
Does she know? Yeah, how does she know for sure that it's Bob? Well, the message said, love Bob. So the danger here is that if Alice is getting a message, this allows anybody to communicate with Alice in secret, but it doesn't sign the message so that she knows it comes from Bob. So what this introduces is the notion of a digital signature. Bob needs to send a message in such a way that Alice is convinced the message could only have come from her. Well, if Alice and Bob know each other, if Bob has some dirt on Alice, there's that possibility, but maybe somehow that dirt became public. The way it's done, and again, the details are not too bad, but in the interest of snow, I'm not going to go through them, is Alice has her stuff here. I'm a huge believer in subscripts. I think subscripts can make things a lot clearer. This should not be P and Q. There should be subscripts on these. What subscript should I put in? What letter? A. These are all Alice's numbers. And so all the stuff here, I should have an A on it for Alice. What Bob does is he puts in the message, Bob chooses his own stuff. And so Bob over here will have his P Bob, Q Bob, E Bob, and D Bob. And the great trick is Bob takes a smaller message X, and he raises X to the secret power dB. And he puts that at the very end of his message. So when Alice decrypts the message, she gets gobbledygook at the end. And what Alice does is when she takes the gobbledygook, Bob has made EB public. Well, this is the same, because multiplication is commutative, as doing it in the other order. And so Bob has now given Alice a way to decrypt a very special message from him. And he can put this in, and what Alice knows is that Bob has made EB public. The only way raising this to the EB works is if this was raised to the dB. I don't know what dB is, but I know that if it's going to work, if I raise it to dB, that's got to be dB. The only person who knows dB is Bob. The message must have come from Bob because it's using Bob's secret code. So this allows Alice and Bob to communicate securely, with Bob able to say more than just love you, but to actually, quantify, I am Bob who loves you. And it's nobody else.
She doesn't even know his code.
She doesn't even know his code.
She just knows the relationship.
She just knows the relationship. And this is just using commutativity of multiplication. So, to do this unit justice is about a week. And so, this is, 20, 30 minutes is not quite a week. This is a quick overview to give you a sense of what's out there and the type of mathematics.
Why is m raised to the ed equal to m on your last line?
Over here is one.
Is one mod.
Right. So the reason this is true, all right, I will quickly show this. So normally you use what's called Lagrange's theorem from cosets and group theory, which I'm not assuming a college algebra course. So I thought about how to do this elementarily. So let's say P is prime, A is relatively prime to P. Yes?
I was wondering if we could use like small prime numbers and see it, if that would help illustrate it.
But that's only an example. So here's a quick proof as to why it will always work. So here's the claim. A to the P is always congruent to A mod P. And then what we're going to do is this will imply A to the P minus 1 is congruent to 1 mod P. Because if I multiply both sides by A, that's the only way I can get here. And then what I'll then do is I'll get A to the Q is congruent to A mod Q. I'll play some games. I'm only going to just prove this in the interest of time and hope that this gives you some rough idea of why things are true. What is the easiest choice of A? I want a number that shares no common factors with P. No. No. There's no prime divides both A and P.
So what's your question?
What's the easiest choice to take for A that's relatively prime to P?
So what happens with 2 and 3?
Nope. Think easier. 1. So is 1 to the P congruent to 1 mod P? Yes. In fact, they're also equal. So now assume 2 to the P is congruent to 2 mod P, dot, 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 all the way up to A minus 1 to the P is congruent to A minus 1 mod P. We're going to proceed by induction. Okay, so let's assume we've proved up to here. If we consider A to the P, this is A minus 1 plus 1 to the P. And now if we put in parentheses, we expand this with the binomial formula. And this is going to be the sum, k goes from 0 to p, of p choose k, a minus 1 to the k, 1 to the p minus k. So these are the binomial coefficients. But because p is prime, the numerator is always a multiple of p. The denominator is never a multiple of p, as long as k is between 1 and p minus 1. So for 1 less than equal to k less than equal to p minus 1, p choose k is a multiple of p. So if you think about what's going on, if I look at 7 choose 1, that's 7. If I look at 7 choose 2, that's 7 times 6 over 2. That's 7 times 3 is 21. It's also a multiple of 7. If I look at 7 choose 3, this is 7 times 6 times 5 over 3 times 2. This is 35. It's a multiple of 7. So all the middle coefficients are multiples of p. So that means this is equal to a minus 1 to the p plus 1 to the p mod p. But by induction, a minus 1 to the p is equal to a minus 1 to the p. So this is equal to a minus 1 plus 1 mod p, which is a to a mod p. So this proves if I take a number relatively prime to p and I raise it to the pth power, I get back my original number. This isn't quite exactly what I need for RSA, but it's damn close. The storm is coming. I see the snow falling. And so what you would need to do is say, well, now, what if I had a to the p minus 1 to the q minus 1 and play that game? So you can play that game, but you can avoid all the graduate algebra by doing this argument and just looking at what's going on here. And this gives you a sense of the mathematics behind RSA. Now, proving how secure RSA is, we're using almost all the mathematics in the book. We're throwing everything at it to try to crack it. And we use a lot of very high-level mathematics to crack it. But the actual description of how RSA works and the actual analysis of how it's used is very elementary. There's nothing beyond high school mathematics here. You use the Euclidean algorithm, you use multiplying, elementary properties of binomial coefficients. You can avoid everything else. So if you have enough time, and again, I will send you the chapters that my colleagues and I have written. In fact, this was co-written with a high school teacher. So he's got a real eye as what do students need to see in terms of writing an exposition. If anybody's interested in trying to do this module in their school, in their classes, let me know. I'm working with the group. There may be resources available to help you with something like that. And there's a lot of great math behind stuff like this. Right? So I'm going to stop the RSA unit here and then